So we'll continue with the properties of the measure we have just constructed. It is actually the Lebesgue measure. We have seen the equality in the case of K cells, but since it is regular, the equality will follow for all other sets as well. So that part I will leave it to you, but let us prove a uniqueness property of the Lebesgue measure. Okay. So that is the property C, which we had written down in the last lectures. So M is the measure which we constructed is translation invariant. Translation invariant. So we know this from the previous construction, but we will prove this for every E in M. So this follows immediately from the regularity properties. So so what we do is define a new measure, okay, define a new measure, let us call that mu of E equal to M of E plus X. Of course, this is true for every X in Rk. So you fix an X in Rk, so let us say X naught, okay. So X naught is fixed, okay, in Rk. So some fixed point, okay. I want to say mu is same as the Lebesgue measure we constructed, M, right. So we have, so if E is a box, mu of E by definition is M of E plus X naught, but this I know is the volume of E plus X naught because it is a box, but volume is translation invariant, right. You translate a box, it will still have the same volume. So it is volume of E, which we know is M of E. So mu of E is M of E if E is a box. So this implies mu of E is same as M of E for every open set E, for every open set E. Because open sets are disjoint union of boxes, right, and countable additivity, disjoint union of boxes, okay. So here we are using the fact that mu is a measure, okay, but that is trivial to see because mu E is simply M of E plus X naught, and so countable additivity will immediately follow from there, okay. So we have mu of E equal to M of E for every open set. Now mu and M both are regular, because Rk is every open set in Rk, because every open set in Rk is sigma compact, okay, and the consequence of Riesz representation theorem. Both mu and M are reasonable measures in the sense that for compact sets you get finite measure. So once you know equality for open sets and regularity, this would imply that mu E equal to ME for every Borel set, for every E in M, in fact, right. In fact, first for E in Borel sigma algebra, and then for all set, then for all E in M, right, because every E in M is just the Borel set and a set of measure 0, right. So because of that. So this is something which we had done earlier. Remember we proved two measures are proving regularity was essentially this argument that if two measures agree on open sets, then they agree everywhere, okay, with regularity of course. Okay, so let us go to the next property D. So this was if mu is any translation invariant. So what does that mean? Mu of E plus x equal to mu of E for every Borel set E and x points in Rk. Okay. So any translation invariant Borel measure such that mu of k, so it has to be a reasonable measure, mu of k is finite for every k compact. Okay. Then it is the Lebesgue measure, then mu equal to some constant c times the Lebesgue measure for some constant c, some positive constant c. Constant. So we have only Lebesgue measure, which is a nice measure, translation in. So it's a uniqueness property of the Lebesgue measure, that any measure which is translation invariant is actually a multiple of the Lebesgue measure. Okay, so let us, how do you prove this? Take let Q0 be a one box. So one box would be, so let's take 0 1, something like this, right? In R2 it would be the unit box here, 0 0 1 0 1 1 and 0 1. Put the constant c to be mu of Q0. So this is a number, right? It's a positive number or a non-negative number. But Q0 is the disjoint union of 2 to the nk 2 to the minus n boxes. Okay. So what do I mean by that? So if I look at k equal to 1, so this is k equal to 1. In the next level I will have 2 boxes, right? So I have 2 to the minus 1 boxes, right? If I again bifurcate them, I will have 4 of them, 4, that is 2 square 2 to the minus 2 boxes, etc., etc., right? They are all disjoint. Since they are disjoint, the measure will add up, right? So if I look at only Q0 and I do this, I will get, if Q is a 2 to the minus n box, then 2 to the nk times mu of k equal to mu of Q0. Remember, the Q can be a 2 to the minus n box anywhere you want. You can translate it and bring it inside Q0, because mu is translation invariant. So if the Q 2 to the minus n box is here, you can bring it inside by translation and the measure do not change. But the Q0 is 2 to the nk disjoint boxes of this kind. So the measure will add up, right? So this is simply writing Q0 as disjoint 2 to the nk disjoint 2 to the minus n boxes, right? But mu of Q0 is c times, it is c, the constant c, times m of Q0, because m of Q0 is 1, right? This is the one box, its volume is 1. But m is a measure, so the same computation tells me that this is 2 to the nk times any same box Q. I write Q0 as 2 to the n disjoint 2 to the minus n boxes. So this tells me that mu of Q is c times m of Q, right? So mu of Q equal to c times m of Q. So what did we prove? We proved that for any 2 to the minus n box, hence for any 2 to the minus n box Q, we have mu of q equal to C times m of q. So, this immediately implies that if E is open, then mu of E is equal to C times m of E. Why is that? Because E can be written as, so E can be written as union of boxes, right, countable disjoint union of boxes. So, mu of E is the sum of mu of qj because they are disjoint, but for these are boxes. For boxes we know how it acts, right. So, this is C times m of qj, but m is a measure and so it adds up. So, this is just C of m of e. But now we know what to do because of regularity. So, from here we simply use regularity to prove this for all Borel sets, right. So, we will have mu of E equal to C times m of E for every Borel set and so for every Lebesgue set also, but that is not important here. So, the only translation invariant measure on the real line or RK with this property is the Lebesgue measure. So, that is the uniqueness property of the Lebesgue measure. Okay. And so, we have one more property, how it behaves with the linear transformations. Okay. So, let us write down that. Suppose I have a linear transformation, suppose T is a linear transformation from RK to RK, it is a linear map, right. So, recall what is a linear map? T of x plus y is equal to Tx plus Ty and T of alpha x equal to alpha times Tx, where alpha is a real number. X and y are in RK. So, that is the statement E. Then assertion is that there exists some number depending only on T greater than or equal to 0 such that measure of Te equal to constant delta T times measure of E. Okay, for every E in M. How will you prove this? So, there are two things here. One is I need to know what is the property of Te so that I can write m of Te, right. So, m of Te will make sense only if Te is measurable. So, let's do this in two cases. So, case 1, suppose T is singular. Suppose T is singular, that means determinant of T is 0. Then, well, from linear algebra we know that range of T is a proper subspace of RK. And so, measure of T of RK, so this is the range of T, right, equal to 0 because it is contained in a proper subspace of RK. So, let's recall that in R2 if I take a subspace, proper subspace, that will be either 0 or a line, and this has measure 0. Okay, this line has measure 0, we did this. So, similarly any proper subspace of RK will have measure 0. So, if I take any E which is in RK, then T of E will be contained in T of RK which has measure 0, this has measure 0. So, it is a subset of a set of measure 0. By completeness T of E will also be in M, right, and M of Te is 0. So delta t in this case is 0. This is going to be the determinant which we will prove. Okay. So we will, let us do the case 2 as well. Okay. So case 2, t is invertible. So you define a new measure mu of e equal to m of t. Okay. So I'll for e in Borel sigma algebra of Rk. So here you have to prove that Te is a Borel set. Okay, if and only if E is a Borel set. So this is easy because T is continuous and T inverse is also continuous. Now mu is translation invariant because mu of E plus x equal to m of T of E plus x equal to m of Te plus Tx, because T is linear, which is m of Te, which is mu of E. So it is translation invariant, and mu of k is finite for every k compact, that is trivial because T of k will be compact, and so by uniqueness property mu of E will have to be equal to some constant which we call delta t times m of E. This is all we wanted to prove. Okay, so we will stop here. So we just looked at some more properties of the Lebesgue measure, how it behaves with the linear transformation, more importantly the uniqueness of the Lebesgue measure with respect to translation invariance. So we will continue this. We will look at more properties of the Lebesgue measure and Lebesgue measurable functions in the coming lectures. More importantly, we will construct or at least explain why there are Lebesgue sets which are not Borel. So we have seen an example of a set which is non-measurable, non-Lebesgue measurable, but we will see examples of Lebesgue sets which are not Borel sets.